Welcome everyone, and thank you so much for joining today for the first of 3 pre-conference panels for our upcoming meeting, Transformative Opportunities for Modeling in Neurorehabilitation, that will be held in a hybrid format the first weekend in March at the University of Southern California. I'm very much looking forward to the sun from rainy Seattle today. This conference is supported by the National Science Foundation Disability and Rehabilitation Engineering Program, as well as the NIH Center for Medical Rehabilitation Research. I'm Kat Steele. I use she, her pronouns, and I am a white woman with shoulder-length brown hair wearing an orange sweatshirt today. And I am part of the organizing team, along with my colleagues Amy Osborne at the University of Washington, and then at the University of Southern California, Francisco Valero Cuevas, James Finley, and our executive coordinator of accessibility and logistics and keeping us in line, Natalie Fung. So we also have a great advisory board who you'll be hearing from during these pre-conference panels, and you can also learn more about them on our website. So a few quick housekeeping items. Closed captioning is available by selecting the CC in your Zoom controls. And if you have any questions or requests today, don't hesitate to reach out via chat. A recording of this session will also be posted to YouTube in the next week or so. All right, so let's get started. Today's session, our opening session, is a broad-ranging challenges and opportunities for computational modeling and neurorehabilitation. And it will be moderated today by our co-PI, James Finley. James is an associate professor in the Division of Biokinesiology and Physical Therapy at the University of USC, at the University of Southern California, where he directs the Locomotor Control Laboratory. So James, I will turn it over to you now.
All right, thank you, Kat, for the overview and the introduction. I'm excited to be here, and I'm glad to see that we have so many participants who are continuing to stream in. So I'd like to start by introducing our 2 guests today, Dr. David Reinkensmeyer, whose primary appointment is as a professor of mechanical and aerospace engineering at the University of California, Irvine, and Professor Nicolas Schweighofer, who is a professor of biokinesiology and physical therapy here at USC, the University of Southern California. So just by way of providing a bit of an overview of what we'll be doing today, we are going to start with a guided discussion. So we have a set of questions that we will pose to both Nicolas and David. And if you have questions as we're going along, feel free to drop them in the chat if they seem pertinent to the ongoing conversation. If you have other questions, we're going to have a Q&A period at the end of our session today, and that will operate as it does in many other Zoom meetings, where you can use your raise hand function, and we will call on you all in the order in which you raise your hands. So that way you can unmute and ask your questions, and we can again get to know each other. So with that, just one of the main reasons why we're having these sessions and the conference in general is so that we can build community and really think about the future of the world of computational neurorehabilitation. So with that, I will start with the first question for our panelists. So I think everyone here received the email and knows that one of the reasons why we have our 2 panelists today is because they were 2 of the main authors on the paper Computational Neurorehabilitation, Modeling Plasticity and Learning to Predict Recovery. So you both did your training in areas known for computation. So Dave in electrical engineering, Nicolas in advanced mathematics and physics. I just found out that was your bachelor's degree. Can you both start by telling us a little bit about your academic journey and what led you to the area of computational neurorehabilitation?
Dave, you start?
Yeah, you start, go ahead.
All right, I'm physics, mathematics, and then mechanical engineering. Then out of my school in France in mechanical engineering, people were making cars and missiles. And after that, I wanted to do something else. So I thought, what am I going to do in life? And I came to the US and I decided to do a PhD in neuroscience. That seems more profound. I studied the cerebellum, and I was doing computational models of the cerebellum. This was my original field of research. And I ended up making very detailed cell models of a part of the brain called the inferior olive. And there were really many, many parameters to hand tune in these models. That was not very exciting anymore. And I was in Japan at the time, and I got this great opportunity to work in a startup to do some systems that would adapt to the person and enhance learning. But in this case, it was declarative learning. So this was the beginning of the startup world in high tech. 2000, everything exploded, and really the internet was not ready for this kind of adaptive learning, where you will get data and tune the learning system to the participant or to the learner. So, this being one reason, and other reasons, I went back to academia where I had my freedom to do what I wanted to do. But then what should I do with my weird background now, correct? So I came and discussed at USC, back to USC. This is where I did my PhD. And, it seems that I could put my motor control, motor learning, adaptive system data together to try to improve recovery post-stroke. So this gave me the job at USC, and this is what I've been trying to do, since I've been at USC in the last 18 years. Dave?
Yeah, for me, it started, I was an electrical engineering at MIT, a major at MIT, and there was an option. This was before there was biomedical engineering programs. But there was an option at MIT back in the 80s for, it's called 61B. So bioelectrical engineering. So you took 3 quantitative physiology courses. And I think I just loved those courses. So it was like, mathematically modeling the sensorimotor system was one of my favorite courses at MIT. And it was sort of in the spirit of Norbert Wiener, who was like one of the first, hey, wait a second, biology can be modeled, like you can make mathematical equations, use feedback theory. So I got really interested in that there. And then at Berkeley, then I started taking neuroscience, still majored in EE, but was able to craft my own sort of thing, neuroscience and robotics, and got interested in robotic rehabilitation there, and sort of built some of the first like really crude primitive robotic therapy devices with Steve Lehman and Pete Lum. And so then decided to pursue that. Postdoc was Zev Reimer at Northwestern Rehab Institute, Chicago. And the one thing I'm going to say, Zev, every time I brought a new robot design, he's like, well, what's it do mechanistically? What's the mechanism or something like that? So what's the physiological? So I came to appreciate the idea that you just can't just build technology. You got to have a reason for it. And it should be based in, sort of fundamental neuroscience or neuropathophysiology. So that then sort of spent career building devices, but always wanting to sort of understand them or model them or find insights into them. And I would say for me, this paper came out of sort of a realization for myself and going to a lot of rehab conferences and going to a lot of robotic rehab stuff, and realizing that sort of no one states their assumption about how plasticity works. And I think I was influenced by Chris Atkinson at MIT as a roboticist. It's like, you don't understand it unless you can build it. So, we were building like throwing robots or hopping robots with Mark Graper. So the idea being that unless you can write an equation down to describe your premise about the way the robot rehab's working, you don't really understand it. So that's sort of my entry point into it.
Great introduction. So Dave, you already alluded to this. So this paper it resulted from what I guess I would imagine is a fairly stimulating colloquium at, Nicolas can correct my French, the Bouchard Foundation in 2013.
Yeah, it's actually Borchard. It's actually Borchard. So it seems like it should be Bouchard, but it's Borchard.
Okay, so my American accent would have worked perfectly there. So what inspired you to write the grant that supported the symposium? Can you tell us a little bit about how the symposium was organized, and just sort of, how it proceeded. Yeah.
Yeah, I can't remember, did you first find about the grant, Nicholas, or was it me? I can't remember.
Can't remember.
Yeah. So anyway, we were, I don't know, actually. I didn't take the time to go review how we were starting to talk about, like, modeling, and maybe were we starting to interact over data sets from Armio Spring in the clinical trial?
No, this is
before that. Okay.
Before that, yeah.
Well, there's a special grant for Southern California professors that we both became aware of, and it's to host a small colloquium in on a topic of your choice in Brittany. So
this is in the, it's when we were forwarded. Oh, here you have it. We were forwarded the link to the grant, and the first thing you see is just this castle.
Yeah.
And they tell you the grant has to be in the castle. It has to be less than 9 people, because this is all you can fit in the main room of the castle. There's only 9 people who can sit there. Here, there's the room. Oh, perfect. So you see the table. People have to sit at the table, and there's only 9 seats. And you have $30,000 for 9 people for 5 days or 4 days. So you have to spend all the money. Oh, this is great, Dave. This is wonderful. So we, so the great things about a grant like this is very easy to get people to say yes to come. We're going to be in a castle, and this is going to be in a 4-star hotel, and we have to eat very expensive meals because we have all this money to spend. So I don't think anybody said no. Everybody we invited came.
Yeah.
So there's some familiar faces here. Can you tell us who joined you all?
Yeah, I think this picture, Svennen, Krakauer, Casadio, this is the runs the foundation, Catherine Lang, Gerquaco, Paulo Bonato, Emmanuel Guigon, Nick Ward, Olivier Remineri. So, and who was starting a large scale trial of Armio Spring. And then Emmanuel I had worked with on my sabbatical in Paris as a computational motor control person. So yeah, so that's sort of, we had this wonderful, you can see how great it was with the big table, and that's my family came. The Tour de France had, I'm seeing if I have any picture of the food. There's a galette, I guess. Well, I guess I can't show you the food, but there was great food too. So the Tour de France actually had just left when we got there. So they had just stayed in this hotel chateau. So it was great. What a wonderful opportunity that, so it was really trying to talk about, hey, could we bring computational modeling to bear on elements of plasticity and learning and rehabilitation? And that was and then we were required to write a paper as in a deliverable for this meeting.
Okay.
So there was a collaboration context to that going on at the same time, because I was doing my sabbatical in France, and I got involved in an ongoing clinical trial with a device called the Armio Spring, which is was invented by Dave. And so they had this clinical trial, and they were typical trial. They were recording pre and post intervention. And it seemed to me like such a waste. There was so much data collected that could have been collected, but it was not collected. And Dave said, yeah, you just turn a switch and you can get all the data. So we asked all the sites to turn off the switch, and suddenly a huge amount of data was coming. So this was going on at the same time. And then this resulted in several papers with Olivier Remineri, with the PI of this trial. Mm-hmm. So this is how really Dave and I really started to collaborate. At the same time, we were organizing this conference.
Yeah, and then for me, actually, on my I took a sabbatical just a couple of years before this conference, and I decided this was the thing I wanted to look at, is could you computationally model, stroke recovery, and so I selected to work with a primate neurophysiologist, Mark Meyer, and then Emmanuel Guigon was there as well in Paris. And so he sort of tutored me on primate neurophysiology, and I made a model using sort of stochastic search as a metaphor for the way recovery might be working as the process that's driving the learning. So that was in and that was sort of wild and out there, you know. So anyway, so when I found someone that was also interested in this, it was reassuring.
We were two. We were actually two for quite a long time, and I remember Dave saying this field is really taking off, and so this is, and I'm so exciting that now we have this conference is generating so much interest.
Yeah.
Yeah. So I want to make a small point for those you know, junior researchers out there. A word that's come up a couple times from both of you was I was on my sabbatical. I think that actually speaks to the benefit of a sabbatical, where you can go and think a little bit in more depth about your future and the things that you find really interesting, and really grow into maybe new areas that you didn't have time to pursue beforehand. So can you both maybe tell us a little bit about how computational modeling has informed your work over the past several years, particularly as it relates to neurorehabilitation?
Go ahead, Nicolas.
Yeah, I think it's not informed. It's my work. It's what I do. Because, you know, maybe for Dave it's a little bit different because he comes from a robotics background, but I really come from a computational neuroscience background. So what can I model, Craig, is always my questions. So it's, you know, my lab it's called the Computational Neurorehabilitation Lab from the start. And I really made up the words based on my background. You know, I'm an engineer, I'm a neuroscientist, and I'm in the neuro and rehabilitation department. So I thought, oh, I can put all these three things together. So that makes it a very long and difficult name to say, especially followed by my last name, but I've stick with it. So this is what we do. You know, we do. So my lab has to be interdisciplinary, and I think this is going to be a common theme. You know, we need to have clinicians. We need to have engineers and neuroscientists. And so that's the key. It's a challenge to make this happen. This is helpful, and USC has been very good and very helpful for me because I have different joint appointments, you know, in neuroscience, BME, computer science, and of course my physical therapy, biokinesiology main appointment. So this is a challenge to get a group like this together to talk on the same language. We know they don't like it. It's everybody's out of their comfort zone. But then you can make something unique by translating, you know, different aspects of the different fields into one new thing.
For me, I'm going to say something else I learned at MIT, which was Mars levels of analysis, David Mars levels in vision. So the idea that you can understand a system at different levels. So one is the computational level. What is the computations it's performing? The second is algorithmic level. What are the algorithms it's using? And the third is the implementation level, is what's the hardware. So that would be like a computer or a set of neurons. And that appealed to me, and that recognizing there's different ways to understand things. So for me on sabbatical, it was about trying to come up. So what I would see when I go to conferences on rehabilitation, robotics, or on rehabilitation in general, is we did this, and then there's always a moment of magic where, like, you would want someone to say the neuroplasticity mechanism that happened, but there's always a moment of magic. It's just like magic happened, and then they talk about the clinical outcome. So for me, it was about trying. So how's it inform my work? Is, you know, on that sabbatical, we had this sort of hypothesis that it's being driven by a stochastic search, which is a biologically plausible learning algorithm. And so that's informed the way I address things. For example, for a stochastic search to work well, it's a form of reinforcement learning, and presumably you have to have a teaching signal, which I think would have to be some amount of sensory information. So in my lab, we've been starting to look much more closely at the role of proprioceptive information and predicting and allowing effective robotic rehabilitation, and have found that it explains up to 40% of the variance of recovery in robotic rehabilitation. So, you know, working with the model, it sort of pointed me, like, it made me concrete, like, what things had to be operating, and then if those are broken, how would that affect, you know, outcome? And then my work recently, just this whole mentality has sort of taken another turn, which is I'm involved in I helped start a company called Flint Rehab, which it sells something called the Music Glove, and the that was developed in my lab. But then these pucks, Fit Me pucks that look like this, you do home exercises with them, like 40 exercises you can do with these. So that with that company, we're getting like, there's thousands of users of this now, and we're getting back anonymized data sets of showing usage patterns. So then it's like, oh, well, now you can use learning or modeling and machine learning to understand who persists in rehabilitation and like who's benefiting. And actually, Nicolas and I are starting to collaborate on that as well too. So, yeah. In home rehabilitation, yeah.
Great. So we actually have a follow-up question that relates, I think, to this very point. The question is about, can you all provide any examples of engineering innovations that have been enabled by computational modeling, and presumably engineering innovations in the world of neurorehab? And how can you maybe talk a little bit about how models might be used to guide engineering design?
I'll start on this one, then you can go.
Okay. Yep.
Yeah.
Please do.
Yeah. I cannot think of anything practical that has come of it yet. Either in terms of algorithms used clinically, for making predictions, or stratifying patients or things like that, or shaping treatment, or in terms of, now we are in my lab because we now believe that proprioception is really important. We've started to develop, focus on innovative ways to retrain proprioception. So but that isn't out clinically available. There's devices and algorithms that we're starting to publish for like doing more intensive proprioceptive training, which I think was informed by the models. But it's that kind of thing. It's like, you got to do it. It's eventually, hopefully, going to lead to something useful. But currently, I think it's still sort of exploratory, and yeah.
Yep, I agree. Just James, I was not sure if you were talking about software or hardware. Clearly, in my lab is more software.
Yeah, I think the question was general engineering. So yeah, we could go either way.
So in my lab, clearly software, but not ready for prime time yet. Hopefully before I retire. I don't know how long I'm going to keep on working. That's the goal.
Oh, so did you were saying that it has enabled some innovations in terms of software?
It is currently, it is currently, but it's not in the market yet.
Is that something you can tell us more about, or is that a
Sure.
Sure.
So we're working on predictive models and optimizing of rehabilitation based on these predictions. The data is really a big issue for us, and so luckily the data and the high quality data, as Dave has been saying for a long time, high quality data is very hard to get. I'm very lucky that thanks to Dave, we're getting all this data coming out of the Armeo Spring, of the Fit Me, but these data have not been, they're great data for many users, very detailed time points. This is great, but these data sets have not been designed, to allow the type of model we want. So we have to go around the missing part. Getting the NIH to fund us for a very high level detailed data, the neural, movements, clinical, longitudinal for many patients is really expensive and really difficult to do. And that's, for me, has been I'm getting ahead of the question here, but it's been the main block.
Yeah, so I'll follow that up, because I think this question of we started with talking a little bit about models for understanding. Once you have your models and you combine those with the data being generated by rehabilitation systems, now you presumably have some insights. And so those of us who are on the computational ends of things, that really excites us. But then you have your clinicians, right, who maybe don't always have that computational background. Do you all have any experience or thoughts about how to bridge that maybe divide, right? Once you have the data, how do you maybe convince the end users, the stakeholders, that that data could be useful to them. If you haven't, if this is not a problem, it doesn't necessarily have to be a problem solved, but yeah, what are your thoughts on that?
To be a bit provocative, I'm going to say that when I give talks, I almost never talk very much about computational modeling. And I feel like it shuts people's brains off, because the rehab world is not used to equations and thinking that way. So it's nothing, and it shuts my brain off too. I mean, it seems like it's going to be boring. That's all I'm saying. When you put up an equation, it seems like it's going to become a boring topic. And so I think it's, and to be honest, what we said earlier, there's very few examples where it's impacted clinicians in a tangible way. So they would be rightly skeptical that this would be relevant for me to now listen to and put the effort in to understand, that. So I think that's an issue. It's a big issue. We need collaboration. So the thought has to be put into how's that ever going to happen given this dynamic? And is it just two worlds that can't meet, or how can they meet? And maybe, there's things like the PrEP algorithm, which is a simple sort of finite state machine, I guess. I don't know, like that's sort of coming in a little bit. At least it's a little bit algorithmic, based on some sort of thinking about the way plasticity works with cortical spinal tract function. So that might be a little bit of a link in the start. But anyway, those are just some random thoughts on that.
Yeah, the equation is tough. Like Dave, I don't have the choice. I have to talk about my model. I have nothing else to talk about. So, so I do show equations, but I show very few. And I really explain these equations very carefully. At least I try to. I think I do okay because my dear colleague Caroline Winstein says that she understands what I'm talking about, and she's a physical therapist. So the translation work is hard. We come from a bunch of engineers, we talk mostly to clinicians, and we have to do our best to explain what we do very clearly, I think, and it's a challenge.
Yeah. I will go ahead and then sort of maybe promote some of what Nicolas has done, because I've seen it where we're in a physical therapy department and he has had students in his own lab, but also has trained students from other labs whose backgrounds are in physical therapy to implement computational modeling as part of their research workflow. And I think a lot of those projects tend to be quite successful. So I think there's some movement in that direction, at least at the level of sort of training of scientists. And now maybe there's one more step to maybe introduce some of these concepts, at least in the terms of measurement at the level of training our clinicians as well. So we have another question in the chat here. So do you all know of any open data sets, so large, big data sets, and to help facilitate computational neurorehabilitation efforts? So things that might allow others to, dive in who maybe don't have access to large scale clinical trial data.
No.
Yeah.
I think it would be nice to sort of, I think there aren't any with fine resolution, but they're coming, is what I would say. Because, for example, OpenCap is a project out of Stanford that's leveraging machine learning for motion capture, which has gotten really, really good. I didn't realize how good it was. And then BJ Fregley, Stroke Grand Challenge, there's another one coming. Data sets. NIH is implementing a data requirement. That's going to help. Studies are using tech increasingly more and more that takes fine resolution rehabilitation data. So that's going to help. And here's another one. So someone else, was that Kat?
Kat dropped that in the chat. Yeah.
On OpenCap. Yeah.
I was just trying to add useful links to what you are saying. So.
Yeah, absolutely. Absolutely. So OpenCap's probably going to be more like it's single session-y kind of kinematics and that inferring muscle forces. So for like standardized tasks, I think like squatting or walking, or that's my impression of it so far. But
we have three chat projects. So this is great. You know, the type of data that especially that I'm looking at is very multimodal and difficult to get, right? So clinical, neural, movement, EMG if you have it. So it's really difficult to get, especially because it has to be, you know, if you look at stroke recovery or neurorehabilitation, it has to be for a long time, over multiple days or weeks. It's hard to get, and I'm excited that people have some data to share. This would be great. Such an advance.
Yeah. I mean, I'm kind of getting excited because people are putting in there. So I was thinking about, you know, chat GPT today, and but just like this, all of a sudden, all this chatbots are doing great. Like they're amazing, right? And what drove that? And it was like, it was driven by the sort of the internet, by all this information about that you could mine through pattern. I'm going to call it simplistically pattern recognition or pattern selection. That you can now mine this massive database off to then sort of mimic logical statements, because there's all this data now out in the cloud. And I'm wondering if we will go the same way now, right? Like we're way behind compared to the internet, but as these data sets get hosted and larger and larger and larger, then it just seems like there'll be more opportunities to find the patterns in them and make logical statements based on them, right?
Absolutely. And including validating your model, correct? So ideally, you develop your model on some data set and you validate on other data sets. We have a paper in the medRxiv when we did that. We developed a model with one data set, and we were very happy to see that, you know, it was, you know, supported by the other data set.
So given that the original colloquium that led to your paper was in 2013, so that's now almost, well, approximately 10 years ago, what changes have you seen in the application of, let's say, computational modeling to neurorehab over the last 10 years? Have you seen, I mean, the field, clearly we have this conference now, how have you seen that development happen? Are there any key changes that you think made this those developments possible?
David, you want to shoot?
Yeah, go ahead. You can go.
I was letting you go.
Okay.
All right, let me shoot. Yeah, so but data, you know, there was no data at the time. So now we have some. The only data we had before was clinical trial data with very few measurements. That's a big thing. For me, and I'm just talking really for me here, I used to do mostly detailed, you know, computational neuroscience type of network modeling. And now I'm extracting these models to very simpler model with fewer parameters that can be estimated from data and do prediction. So for me, this is being really, you know, I'm not sure about the field in general here. This is really my thinking. So extracting, you know, the essence of the more complex models, you know, and then try to make very simple models that we can individualize from real data, and then do prediction. So, and people have did this in the past, right, with simple regression model. But if you have a simple regression model, you know, just imagine the slope, you can only measure things that go up or go down, right? So as we know, plasticity, and maybe we have more conversation about this later, is a dynamic process, right? So you're going to go up and down at different time scales. So clearly a simple regression model is not going to work. Whereas our dynamical models from the neuroscience, you know, they were more dealing with this kind of thing. So we can extract that. And then if the models are small enough, given the data, depending on all the data you have, you can maybe, you know, estimate the parameters to make accurate predictions in the future. So this has been really my big, you know, change of thinking in the last few years.
I agree with that. And I wanted to say something too. Another heart of this dynamic is the force field literature, I'm going to call it motor adaptation force field literature. And I did some studies in that, and oh my gosh, it's impressive the level of mathematical detail that can explain adaptation to robotic force fields. Incredible, right? Then you put on your rehabilitation hat and you're like, it's almost completely useless. And I'm sorry, I'm being provocative here, and that's probably going to offend a bunch of people.
I like it.
Yeah, and I'm not denigrating the work. I think it's important, but when you think about, wait a second, this is a process that's happening very relatively quickly. Rehabilitation is not like, it's a different time constant. And but it's inspiring. It's sort of like an existence proof that you could take a plasticity process and just like understand it so detailed, with detailed predictions, mathematically based. So I think that was in that dynamic of being inspired but frustrated by my exposure and involvement in that field. So that's not exactly answer your question, but, and then I'm not going to answer. The other thing is, I'm going to say what hasn't changed. My feeling is still that, and I almost want to put a challenge out to everyone that's going to this conference. Like, if you're going to talk about learning, you know, put an equation behind your magic. Like if something in your study had to do with a rehabilitation outcome that was driven by plasticity, make a statement in your talk somewhere about, this is the equation I think might be operating. Because I don't think that's being done very much still. I think that has not changed very much.
Yeah, but I think just to follow up about the motor adaptation literature. Just a little bit different from Dave. This, for me, from a theoretical point of view, the idea generation here is very important on the modeling side. So what can we learn, you know, from these guys and in this literature, and can we apply? And I think several of us have done that, including Bob Scheid, who I saw earlier. Hello, Bob. You know, and so this was we can really learn from the way they do things to try to, you know, learn from them and develop our own models. Even if motor adaptation at the end is probably not going to be so helpful for rehabilitation. I agree.
Yeah, that's good. Thank you for clarifying that. And I agree. I totally agree with that statement as well.
And I'm also interested, Nicolas, in your thoughts on whether, you know, funding pressures have also helped drive that transition. So for those who were maybe, let's say in the early 2000s, more interested in modeling motor adaptation, when you're applying for grants, you need to explain why we need to be studying these processes. And there seems to be maybe a logical push toward trying to apply computational methods to neurorehabilitation. So I'm wondering if that pressure has also sort of moved the world toward more computational modeling. Maybe.
I don't know. No, maybe.
Oh.
Yeah, I don't know. I often put a line in my grants. Yes, the link. Maybe a little bit hand waving. Yeah.
Yeah. So we have a question in the chat, which I think also speaks to maybe one reason why computational modeling has grown over the last decade or so. So I'll just read the question. This is from Juan Carlos Perez. There's been significant research on biomechanical modeling of movement, for example, with OpenSim. How can these two branches, and presumably that's the biomechanical modeling and rehabilitation, benefit from attending to the results from studies of the, I guess, more from the biomechanics world? So I think
James, you're the person to answer that question. This is for you. This question.
Yeah, so I'll actually just use this moment as a plug for our next panel, which is really about this topic. So I'm most fascinated by this intersection between neural control and biomechanics. So the world of neuromechanics has been coined by, I won't say who coined the term, because I'm not actually sure, but this idea of how do we take these models of biomechanics that have been developed over the last couple decades and then start to add some control there. because that's really what we're dealing with when we're talking about, neurorehabilitation and movement. So I know there are some people here in the audience who do some of that work, Kat as well. And I think there's a lot of opportunity there, which we'll hopefully be diving into in detail on our next Zoom session, as well as throughout the conference. So I think to answer the question, I think one thing that's still remaining is really bridging, again, the sort of literature gap between those who tend to focus more on biomechanics and those who tend to think more about neural control. I think there's often a disconnect between those two communities, and that's one reason why we're trying to bring everyone who's here together for this our conference in a few weeks here.
Yeah, and
so we have
go
ahead.
Not to sound like a broken record, but then adding the third group of people that's interested in neural learning on a long time constant. Because I think neural control is different than sort of looking at, evolution of things over long time constants. Anyway, and just a shout out to BJ Fregley too. I think he put in the chat like exactly what Juan was talking about, which is he's done a lot of biomechanical modeling, is trying to extend it into like modeling stroke recovery now, I think. So, yeah.
Yeah, we're looking forward to hearing more about that stroke grand challenge. So we have a couple more minutes here before we open up for other questions. So I think, and with maybe the last question, so there are a lot of junior scientists here, some graduate students. What recommendations might you all have for trainees who are interested in this research area of computational neurorehabilitation?
Take more math and statistics, and and keep on reading and reading and reading. This is tough. We tried 3 fields. We have neuroscience. I'm talking about neurorehabilitation here, and engineering. You have to love learning and reading, because it's tough to be on top of this of more than 2 fields, and now we have 3 fields here. So it's tough, and it's always you're out of your comfort zone when you talk about the specialist in each zone, correct? Because they know everything very detailed and very well. So keep on reading, and get your math. This is my mom. My mom had a PhD in physics. She said, "Get your math and get your math." And then everything is easier, because some of these problems are difficult. Optimal control, is very hard. Mechanics is hard. So it gives you a good basis. That's my recommendation.
And I'm going to say something too, like when I applied for faculty positions, my selected area was robotic rehabilitation, and it was in exactly 0 job advertisements when I applied. So there's no one was targeting a hire in robotic rehabilitation. And I applied to probably 150 places and got like 2 offers over the course of 2 years. So I feel it's somewhat analogous right now. I doubt you're going to find a job advertisement in computational neurorehabilitation, or maybe probably in modeling, maybe more so. But you can see that's kind of the thing, though. Like it should. I do think it should take off at some point. Maybe we're just waiting for those data sets to get larger and more available. But so for career advice, it seems to me like a good field to go into, but you're going to have a hurdle potentially, because it might not be sort of explicitly sort of targeted at this point, for hires. So. Mm-hmm.
Yeah, I'll add one piece of advice, and only because this is advice I received from Nicolas, which is, one thing I really like with computational models is that if you are planning to model a behavior, you can also simulate that behavior first and then test your model on simulated data. This is something that I've found to be a really powerful tool. It helps you really think through, or powerful process. It helps you really think through what kind of data do you need to accurately test your model, what things are you able to infer, what things can't you infer. But that process, and you can do that process with actually no data. So the question earlier was about how do we find data. The nice thing about simulation is that you generate it, and then you can actually go through the same sort of thought process that you would if you had real data. So, and then start simple. That's the other piece of advice that we keep coming back to. So with that, we have about 15 more minutes left. So now we can open up for questions that the audience may have. Feel free to use the raise your hand function under the reactions button here at the bottom of your Zoom window, or you can send questions via chat, either way. Okay, so Grace, do you want to start us off?
Sure. First, I want to thank everyone for joining in this pre-conference session. It's wonderful to meet you, David and Nicolas. I was really I really appreciated the candor to which you responded to some of what is computational modeling done for engineering innovations. And what really troubles me is that, do you believe that high fidelity computational model actually can and should exist? And if we could only overcome this cultural barrier, that there would be sort of a useful conversation that one could have with a clinician to actually start the conversation. It sounded like the conversation hasn't really started in a meaningful way. And I just want to get your assessment of whether or not you think these comp neural models are at a point where we can actually achieve the fidelity we need to be able to, to make clinical types of recommendations.
Right. I mean, my own impression is they are not at the level yet that, and the barriers are availability of data, definition of like what they should be predicting that would be useful to a clinician, which is a constraint also by the way the healthcare system operates and the rehabilitation system operates as well. So I think that, I mean, was it Field of Dreams? If you build it, they will come, or whatever. Like, if you have like a really cool predictive outcome that could tell you, hey, do this with this patient because they're really going to benefit from it, and I'm about 85 to 90% sure of it, that could be very powerful. I think, the barrier of the interaction of the clinicians could then be overcome if there was a powerful result like that. But even like prep is, in my understanding, it's this is, for people who don't know, it's a sort of an algorithm to predict the potential for recovery versus compensation, focusing on recovery versus compensation for upper extremity after stroke, based on behavioral signs like moving the shoulder and hand, and also potentially a TMS signal, I mean, motor evoked potential. And even that, when it's been applied and used clinically, but when it was sort of tried to be used and verified at a different lab from the one that was developed in, my understanding was the prediction capability went way down on it. So yeah, that's kind of a long-winded answer, but I don't think we're there yet. I think we can get there. I think when we're there, it will drive things much more naturally because there'll be obvious utility. It'll move out of the research stage, fundamental research stage, into the utility stage. So yeah.
Chris, I think I have a little different answer, complementary to what Dave said. When you talk about fidelity, I think about two types of model and two types of fidelity, right? So I distinguish both what I call qualitative model, that are complicated models that try to explain the neuroscience and the behavior and the plasticity. And these models have many parameters, and they could have high fidelity to the neural process. And so they don't make quantitative prediction on how specific patients are going to recover. So these are much smaller model that then we care about fidelity of the prediction with the small models where we can estimate the parameters from actual data. So I think there's two branches, and they are complementary because the high fidelity neuroscience model inform the smaller predictive models. I think so. Two types of fidelity here. The computational model, the complex model, the qualitative models have make predictions that we can test in in the clinic, in clinical trials. The other models, we're getting there with the data. The fidelity is depending on how much data we have, and we're also making progress. So I'm hopefully, I'm a little bit optimistic that things are improving quite fast these days.
Okay. So we have a question from the chat from BJ Fregley, and I think this is a nice question that will spur an interesting discussion here. So do we necessarily need to be able to model or simulate the plasticity process, which is potentially really difficult, to be able to use personalized computational models to predict how we might induce plasticity, for instance, using rehab robots? So I think this has to do with outcome versus process, right? So can we use models to predict and improve outcomes without necessarily modeling some of the underlying processes? And BJ, you can correct me if I'm wrong.
I mean, yeah, no, I mean, it's kind of relates to what Nicolas was just talking about with the two types of fidelity. I think if I understood that correctly, but also it relates to concepts of like AI versus explainable AI, for example. So could you make predictions? Most certainly. Is there utility in trying to understand the mechanistic basis of the predictions? Most certainly. And I think in the long run, that might be helpful to drive progress, but that's my perspective on it. Yeah, you can follow both tracks and hopefully they'll be complementary.
Yeah, there's always tug of war between the engineer and the scientist in me, correct? So we want to do the best prediction possible. Maybe, AI would give you a benchmark, recurrent neural networks or whatever, give you the best typical benchmark. But of course, we want to understand why things work the way they are, correct? So we like to extract the science and model processes. So it's for me, I have to be frank. There's always a tug of war in my head and research here. What are we doing? I think the best AI prediction model, we don't care about the science, or we care really detail about the science, and then we lose on predictions probably. So this is something you have to decide for yourself what you want to do.
And something too, I think with Nicolas, some of his models, for example, are at a sort of systems level finite difference equations, right? And so they're sort of predictive models with structure, but then he's able to put names to parameters. Like one that comes to my head is confidence. And confidence then becomes a mechanistic explanation of usage. Like it's a psychological quantity that's sort of being modeled and correct me if I'm wrong here, but so you're able to do this sort of predictive model, but then by seeing the parameters, you sort of name things and get an understanding. So, yeah, even at a high level is what I'm saying. You don't need to model individual neurons and Hebbian plasticity particularly, for example, but you could then see like back to Mars levels at the computational level or the algorithmic level, seeing, parameters that mean something, rather abstractly.
Yeah, I think these discussions apply to computational modeling in sort of all domains of science, right? And not just neurorehab. All systems you can model at different levels, and there are reasons why you would do that depending on what problem you're trying to solve and what you want to understand about the system. So I think there are a couple comments here. Okay, yeah, this was Jim Patton, again, talking about the need for a wide range or diversity of models, that he was focusing really on time scale here, right? So models that explain things from moment to moment versus days or months or years, as you might want to do over the course of rehabilitation. Any other? So we have a question here. So
Ralph Nicken has an interesting quote here that might be, can I read that one? Or James, you?
Before it.
It says, computational modeling is like abstract art. It may not be a literal representation, but it takes you through the composition in with a different set of eyes. That's an interesting analogy. you know?
Yeah. Yeah. I mean, I think a related point is I think there's real, when we talk about kind of basic science, we use that term quite often. I think going through the problem solving process is often really helpful in ways that you can't predict ahead of time. And I think that's why we fund basic science.
But if I could add to that, I think you have to have examples where you've done the modeling, and you've actually brought them back to a truth that they missed in the first place. And that was my analogy to abstract art.
Yeah.
Yeah.
Mm-hmm.
Thanks, Ralph.
And another thing, this is a little bit different than the abstract art, but I really like the abstract art thing. But the another thing too, just to say, is that when you do write down the equations, then it forces you to check your assumptions. Like, oh, wait a second, I have to say something. I have to define that variable or say something about the way that works, in order for this whole thing to be a complete computer program. You know.
Yeah, there's in the paper actually mentions that very nicely, and I think Dave, you wrote this part. You have to put everything together, and you have to think about time, and you have to see how the variables interact. That really forces the researchers, I think it says in the paper, to understand. Maybe we should read that. I should read that. Let me try to read that. However, what is lacking is the integration of the processes which operate at widely different spatial and temporal scales. Developing computational models of rehabilitation will force researchers to make these processes and their dynamic interactions more concrete. I think this is a great quote.
Yeah.
All right. So we are running out of time here. So we won't have any additional questions from the audience, unfortunately, but feel free to, again, join us for future both Zoom sessions and our in-person conference. What I would like to end with for both our panelists is maybe could you both speak to what you hope we'll get out of this conference? So what excited you about the conference? What do you hope we might sort of come to, or what opportunities might we identify by the end of our meeting in a few weeks here?
I could go, and then let Nicolas conclude it. Yeah, synergy. I'd just say one word is synergy would be great. It's a small enough conference, I think, and I was super interested in all the abstracts I read. So I believe that it's a great opportunity for synergy.
I was going to say connections, but synergy is a better word. Thank you.
It's almost as if scientists are afraid to say synergy. What is this?
Ooh, this is a loaded word.
Yeah. Yeah. So I mean, I think I would agree as well. As I won't put words in the other organizers' mouths, but I think that's what's most exciting about what we're doing here. So Kat's going to help us wrap up with some final words here.
Yeah, so everyone, please join me in giving a quick round of applause for James, Dave, and Nicolas for being our first group for the pre-conference panels. We really appreciate their time and sharing everything from the European conference that we're all jealous of, but to all the lessons and opportunities for computational modeling and neurorehab. As a reminder, our second one of these will be next Monday at the same time, 11 a.m. Pacific, 2 p.m. Eastern, and we hope you'll be able to join us. All these recordings will be made available on YouTube afterwards. If you have any thoughts or items you want to add to the chat, we'll be saving the chat as well. So we'll make sure to keep and collect those at the end. I see some great things coming through. But that's all for today, and we hope we will see you all again next time. And thank you again to our moderator and our speakers for their time. So goodbye, everyone, and we hope to start the conversation strong on this.